When I first went there as a grad student, there was this field called Munn Field, and they've done away with it now, but students could go and park there up to like a day ahead of time. And they were setting up like tents, big tents and couches and pool tables and pinball machines and all kinds of stuff. It was fun, but they got in a little trouble, so they took that away from them. But it was a good time. I enjoyed myself. The weather was absolutely perfect. Saw all my family and friends. It's all good now. The game was not so good. We got spanked quite badly, actually. It was a little embarrassing, but it's bound to happen from time to time.
Didn't they beat Notre Dame the week before, though?
They did.
That was a pretty impressive win.
Yeah, it looked so at the time. Notre Dame's not looking so hot this year.
They suck this year.
They've lost 3 now.
Ron Kelly loves Cincinnati. So.
Ryan Kelly's kind of a scumbag, so.
In this area, that's the general consensus.
So is Butch Jones, but I actually like him now.
Thanks for getting back to me with that notation. I kind of finally
Oh, yeah.
understood it my own way.
Good.
It's like, I'm going to drop a message.
Yeah, no, it's not a problem at all. I think I got it when I was out of town, so I didn't reply till I got back. But, yeah, glad it worked out.
So the exam is next week, right?
The exam is, no, a week, wait,
Next Thursday.
next Thursday.
Okay,
you are
so
right.
that's on chapter 3, right?
That's gonna be the large chunk of chapter 2, and then probably chapter 3. We'll have to see how we do in terms of time. But chapter 3, we may as well get started. Welcome back, everyone. Chapter 3 is actually a significantly shorter chapter than the previous 2, so I don't expect it to take us a whole lot of time. A couple lectures probably be enough. So if we do it, I would think we'll finish 3 by the end of Monday, or by the end of Tuesday for sure. But we'll see. Okay, so welcome back. Hopefully everyone's having a good week and all that. It's nice that the weather's cooled down some. It's always a plus. Snow. I don't know, you guys got any questions about anything as we get started?
When is the clipping due?
Oh yeah, my announcements. So the clipping 2 is going to be due next class period. So that will be Thursday. A reminder for everyone what the clipping is. You go and find a news article and you write a one-page summary of it. And I just thought it would be and that one-page summary, half roughly, is what the article's about, what it says, and so forth, and the other half is your response to it, what you think about it, what you found interesting or not interesting about it, whatever you want, basically. And ends up about a page. That'll be due Thursday, and then Thursday during class, I'll ask for volunteers for anyone who found anything interesting and they want to share with the class. That way, you kind of see other stories you didn't see yourself. It's kind of useful to see the scope of different stories that are going on and so forth. So that'll be Thursday. I think we're all good with that? Okay. Other announcements on my list. Exam 2, as we just said, will be next Thursday. In terms of content for that, it is going to start with the experiments from chapter 2, the gold foil experiment, the oil drop, and the cathode ray experiment, and then go forward until we get to what we get to. I would expect us to be able to finish chapter 3. We've got today's lectures, Thursday, most of Thursday, and then Tuesday before the exam. So I would expect us to make it through chapter 3 in that amount of time. Chapter 3 is a shorter chapter than the previous ones. I don't think any of chapter 4 will be on the exam. That would be a bit ambitious, I think, but we'll see. You guys probably don't want that anyway. So that's what we're looking at for that exam. Format and everything will be the same. Finally, extra credit for exam 1. I know I gave extra credit for being late that day, and I still feel bad about that, and I apologize. But as a matter of principle or whatever, I always give extra credit after each of the exams, and I don't think it's fair not to give you guys that option just because I already gave it for being late. So on Blackboard, if you go in the assignments folder, there's now a folder that says extra credit. And on that extra credit, actually I guess I could just show you real quick. In that folder, there's extra credit for exam 1. So if we go to the assignments, extra credit exam 1. Now what this is, it's a crossword puzzle based on the periodic table. So I'm asking you for the extra credit, which is going to be 3% of on the exam score, so it'll be 6 points because it was 200 points total, so 3% is equal to 6 points. Print it out and then bring it in. You can either fill it out in the PDF itself or you can print it out and then just write on it. It doesn't make any difference to me. So this is the file. And all of the clues have to do with the periodic table. And we're getting into the periodic table today, so this is why I've been holding it until now. So it'll be extra credit exam 1. So for example, 1 down says I have 26 protons. So what element has 26 protons? Iron. Iron does. Okay, that's iron's atomic number is 26. The atomic number gives you the number of protons. So iron, so it would be iron. Now, some of them you already have the material for, some of them you do not, or some of them I don't expect you to know at this point. So I'm not going to make this do. Well, it's chapter 3 material. Chapter 3 may end next Tuesday. So let's make it do a week after the exam. Okay, a week after the next exam. That will give us plenty of time to make sure we get through all the periodic table material, and then you'll still have time to do it. I don't think it'll take you very long. Right? It usually doesn't take students a long time to do it. But that's the idea there. Where's one that you may not know yet? Yeah. Oh, nitrogen family with 16 neutrons. Right now, you guys don't really know what the nitrogen family is. Nitrogen family is the column where nitrogen's the top of. So this column and every column of the periodic table are called families. And we'll get into that probably today or next time. But this one's named by the nitrogen at the top. So it's one of these elements right here as you go through it. And we'll learn about that. There's a bunch of those mixed throughout the periodic table. All right, sound like a plan? Yeah, okay. Sneezing and coughing going on. I'm gonna take a step back. Yeah, it's allergies and things have definitely been enforced. Okay, yeah, that's that. Okay, cool. Okay. And as I said, normally I always give a chance for extra credit after each of the exams. So there'll be a different one for the exam 2 as we go through it. Okay. Yes, finally I'm going to ask, do you guys want the lights on or off? I've been doing it with off just because of the heat and stuff, but today it's not quite as warm. Kill the lights. Did I ever tell you guys a story about my physics class when the professor used to wake students up? So, when I was, actually it starts earlier than that, when I was in high school, there was a teacher that walked around with one of these sticks, and if you fell asleep on your desk, he would come by and just whack it as hard as he could to scare you. And he kept doing that until he accidentally hit a kid once, and then he had to stop. In physics, in my undergrad was a little weird because the classes were really small. I think there were like 1,400 students at my undergrad, so smaller than some of your guys' high schools probably. But we had physics classes like 6, 7 students, and if you fell asleep in one professor's class, he would throw things at you, just like markers and stuff, and throw them at you. And one time a student wasn't really asleep, and he thought he was, so he threw a marker at him, and the student just reflexively grabbed it and like chucked it back at him. Everyone laughed. We thought it was great fun. The professor, not so much, but it was his own fault for throwing it. So I always think of that when I shut off the lights during class. I'm not going to throw anything at you, by the way. Honestly, I don't particularly care. Okay. So last time we finished up chapter 2, right? So we talked about the quantum model, placing electrons in the orbitals and making sense out of where they were. We also talked a little bit about how that plays into the periodic table with the s, the p, the d orbitals, with where you're placing the last electron. So in chapter 3, we're going to continue on with this discussion of the periodic table and look at it more closely. The first part of the chapter, and that's what we're going to spend most of the time on today actually, is the development of the periodic table. Where did it come from? You look to the walls and you see the periodic table, and these have been the periodic tables that you guys have seen your entire lives. Okay, I've seen my entire life and everything, and it's just kind of the way it is. But it hasn't always been that way. And where does it come from is actually a very interesting story in terms of chemistry. Remember we talked about the Bohr model and the quantum model as well were both developed independent of the periodic table. They weren't looking at the periodic table and then doing the math to explain it. They were done from the mathematics point of view. The periodic table actually was done from a properties point of view, and they end up at the same point, which makes them even more useful in regards to one another. So once we talk about where it came from, then we're going to talk about how we use it. But this is our modern day periodic table here. You've got this general square. Down here in the bottom, you've got these 2 rows in the bottom, but we've talked about how they actually sit in these positions here. The reason why we don't draw them there is because then the periodic table would be twice as wide, and it would take extra paper and width to actually be able to have it all drawn out. So for convenience alone, we simply draw them down below. Now we've got different parts of the periodic table, and later on we're going to learn a bunch of different parts. But one that we can see on this graph very quickly, or this overhead, is the fact that we've got different colors for different areas of the periodic table. Now these are the s block elements because your last valence electron goes into an s orbital in this. So it's either going to be S1 or S2. This whole column is S1, this whole column is S2. They also have a different name. These, in this very first row, are called the alkali metals. The second row are called the alkali earth metals. In the course, we're not going to learn the names of all the different families, but there are 4 that I'm going to want you to know, and these are the first 2. The alkali metals and the alkali earth metals. Now, alkali metals. Almost every one of you have an alkali metal based thing on you right now, and that's your cell phone. So lithium batteries are alkali batteries. That's because the alkali metal contains lithium, so alkali batteries are the ones that contain these elements right here in different ratios. Now normally lithium is the one that's used because it's the lightest. So all of our phones have rechargeable batteries in them, and almost all of them, actually I think all of them probably, are made out of lithium. And then lithium is used to do the recharging and so forth. And that's nice because it's lightweight and it works relatively well. The problem with it is if you overcharge it, then you release hydrogen. You guys all heard recently about the phone that started on fire, right? There's a phone that was released not too long ago, last couple months, that overheated and would actually start on fire in very limited cases. So what that is actually is the lithium battery releases hydrogen, and hydrogen's a flammable gas. So all the electronics and heat was enough to kind of ignite the hydrogen, and then it starts burning as it goes through it. It can happen to any lithium battery if you overcharge it way too much, and that's probably the reason why. Yeah.
So if you like leave your phone plugged in for too long, obviously you're doing damage to it, right?
Well, phones themselves have programs in there that say that once you get to a certain point, they stop charging.
Okay.
And that's actually really, really important because of what you're saying there. I have an, what was it, iPhone 5, and if you would leave that plugged in, I found out it happened to me. I left it plugged in, and it was charging, and it didn't shut off, and it kept, the hydrogen kept building up, and it basically inflated like a balloon, and the front of the screen popped off. And I could just peel it back and look at the inside, so it was kind of cool to me, but that's because I was done with the phone. Okay, it was a while. But that's a normal problem. So lithium batteries do have the drawback of creating hydrogen, and then you got to do something with it. You either got to store it and recapture it, or release it somehow. But if you release it, you actually lose the recyclability of it, the recharging of it. Yeah, actually I had 2 iPhones. So those are the alkali metals and the alkali earth. The other 2 that I'm going to want you to know, over here on the other side, we'll have official slides for this later. This is called the noble gases on the last one, and those are going to become really, really important when we start talking about why elements and atoms do what they do in reactions and so forth, the noble gases. And then this row here are called the halogens. Have you guys ever used, can't talk today. Have you guys ever heard the term halogens before? No? Okay, it's used in lights. So halogen lights, like halogen headlights and so forth, like a headlight in your car, is largely halogen based. So it's one of these ones actually doing it. They do have noble gas headlights in cars as well. Have you guys ever gone down the road and seen like a really, really blue, like one headlights that look different? That's probably because that car is using a noble gas for their headlights. And I guess nowadays they do have LED headlights too, which is a totally different technology. So this periodic table really just kind of shows the different areas. These are called the transition metals. These are your P elements here, and we'll go through and talk about it. and what they all mean and so forth. At no point in the semester am I going to have you guys remember the properties of one given element. But by understanding the periodic table, we can understand why certain elements act the way they do based on trends and so forth as we go through it. Now, if you ever want to look further into elements or periodic tables and so forth, there's a very good website online. It's called webelements.com. And you can go there and then click on each individual element. And what will happen is it'll bring up a page talking about that element. So, if I jump over to my web browser again, we'll choose aluminum because it's my favorite element. And you go in and you can see all different types of information about aluminum. Properties, the history of it, where it was discovered, things like that. There's your history part. Periodic table information and so forth. So you can go through. And it's got all of the different ones. Gallium, see the same type of thing here. So you can very quickly find out information about the periodic table from this Web Elements website. And I just wanted to point it out because I think it's useful in case you need information for some reason. So this is our modern day periodic table. It is not the only periodic table that's ever been in existence or even in existence now. You can go online and just type in alternative periodic tables and it will list a whole bunch of them for you and show you different images and so forth. Here is a random 2 that I grabbed from online. And you notice very quickly that it doesn't look anything like the periodic tables we have hanging on the walls. So what these are is they're differing approaches to organizing the elements to show some property. This one, for example, breaks it into the different groups. So if you look, all of these pinkish ones, these are the transition metals. So it gathers all the transition metals together. Here are the ones that are down at the bottom of the periodic table in this branch, and then your regular ones here as you go through. This one, to be honest, I haven't figured it out yet. It's just a curl. I guess I kind of have. It's a curl of all the different elements in the order that they're in. Now that order, it can be in mass or atomic number, and we'll talk about that, why that's important a little bit later on. But there are different ones. Usually, the alternative periodic tables have a specific purpose they're looking for. So someone may make a periodic table to help explain conductivity, how well electrons travel through a metal. Or there's periodic tables having to do with the different properties in metallurgy, like why some elements mix better than other ones and so forth along those lines. But those are generally specialized cases. The ones that we have on the wall are by far the best ones overall. It may not show one particular property as well as another one, but as a general information source, it does much, much better than all the other ones. And that's why we use it all the time. So just to remind ourselves a little bit about atoms and so forth and how we're going to go about talking about them, we are going to use the Bohr model for our discussion as we go through here for the most part. So if we look at lithium, an atom of lithium, lithium is number 3 on the periodic table. So it's going to have 3 protons. The mass is roughly 7. So if we have 3 protons and a mass of 7, that means we're actually going to have 4 neutrons associated with it. And then we've got our 3 electrons going through. Remember that this electron here in the outer orbit is called a valence electron. I know I've introduced this to you a couple times, but it's going to become really, really important as we're going through things. And to tie the Bohr model into the periodic table, you can simply look at the position of where lithium sits and then make sense out of that being 2 rows down. So it takes 2 orbits to draw the Bohr model. The first column over, meaning that it's got 1 valence electron. Yeah?
Where did you get the 7 from?
Okay, so I looked to the periodic table, and the mass is underneath the given element, Never rounded this one.
6.9?
So 6.9, so I just rounded it to 7.
Okay,
Just go ahead and round it to the nearest whole number, if nothing's given to you specifically.
okay.
Any other questions? Okay. So where does the periodic table come from? There's a lot of different stories, but we've got to first look at where we were in terms of chemistry when this was discovered, or when this started working, when he started working out. Now, the inventor of the periodic table is given credit to a scientist named Mendeleev, and he was a Russian scientist. And if you read stories about his coming up with a periodic table or deriving the periodic table, oftentimes you'll read that it came to him in a dream. I don't really believe that it came to him in a dream because it builds upon previous people's works. Okay? And we'll look at 2 of these examples in a second. But because it builds upon other people's works, I don't think it just all of a sudden randomly came to him out of nowhere. Just like all science, a scientist does an experiment, understands things, and then other scientists takes that understanding and continues on and builds upon it. And then the next scientist builds upon that, and the next so forth and so on. And that's the same thing as this by a lot of different ways. We can actually trace this all the way back to Dalton's atomic theory and his work trying to understand atoms and so forth and building directly upon that to get to this point. But I'm going to skip ahead a couple slides here and then I'll come back just because I want to talk about this for a second. So this work was done in 1869 roughly, and at that time period 63 elements were known. So if you have 63 elements, you know their colors, you know the density, you know their masses, atomic masses, relative atomic masses and so forth. How would you go about organizing it? So my analogy to this is, I can never remember. How many cards are in a deck of cards? 52. Okay? Now, when you were a kid, did you ever have the unfortunate incident of playing 52 card pickup with someone? You know what that is? Okay? So I remember playing with my uncle, and he said, Brad, do you want to play 52 card pickup? And I said, yeah, I'd love to. And he just took the cards and threw them all in the air, and they made a huge mess, and he said, okay, pick up the 52 cards. Okay? That was kind of our relationship at the time. How would you organize that deck, though? If you take your deck and completely mix it up, okay, how would you organize it back together? Suits would be one option. Okay, you could do suits. What else could you do? Color, numerical order, all of these different things. So in your deck of cards, you've got different cues that allows you to organize things. The same with elements. We have 63 elements. They're in different languages. They're from different parts of the world. No scientist had touched all 63 elements by any means. We do have information, but sometimes that information is not shared very well. So imagine in 1863 or 1869, I discover an element. How can I tell my friend in Italy about that element? I can write a letter to him. Okay? That letter's going to go to him, and he can then know about the element. But then how does another scientist find out about it? Well, one of us has to send a letter to him. Okay, and so forth and so on. There were magazines talking about scientific advancements, but they were specific to individual countries. So if someone was in Russia, it was very unlikely they knew about the work done in Italy until it became really famous, or the work done in England, in Spain, and so forth. Plus, you've got language barriers. You know, we didn't have travel like we've got now, and we definitely didn't have Google Translate or anything like that to take an article and translate it into another language. When I went to grad school, so 20 years ago, more or less, a lot of schools still required that to go to grad school in chemistry, you had to know German. And that's because a lot of the science publications in chemistry were done in German. So they wanted you to be able to know German so you could read the scientific work from past time periods. I can't speak German at all. Most schools didn't enforce it, and it's now gone away. because of the various translations and so forth. But think about it, 150 years ago, what it would take to share all that information. So there are certain bits of information we know, and we have to figure out how we're going to go about organizing it. So they would try color, they would try densities, they would try atomic masses, all of these different types of things. And the one that seemed to work the best would be atomic masses. So a couple early attempts to organize are shown here on the board. So the first one is the law of triads. So what does triad mean? So 3, right? 3. Now, what that actually means in terms of chemistry is when we're looking at the elements, oftentimes there are a grouping of 3 elements that contain the same overall property. Now we can see this in today's periodic table. Now remember that wasn't around back then, by the columns. So elements in the same column exhibit the same property roughly. So the first column, for example, reacts violently with water. So at the time period, we knew, let's say, lithium, sodium, and potassium. We knew those 3 elements existed and they've been studied. They all react similarly, in a similar manner to water, and there was a grouping of 3 of them. So when we looked at the masses of these, we saw something actually very interesting. If you take the lightest element and the heaviest element from this grouping of 3 and average their masses together, so if you take 7, add it to 39, divide by 2, you end up with 23. This number that you find matches the mass of the middle one. And the same thing can be done with calcium, strontium, barium. Calcium being number 20 on the periodic table, strontium being 38, barium being 56. 40, 137 divided by 2 gives you 88.5. Strontium's mass ends up being 87.5. So the law of triads said that you can take the masses of these lightest and heaviest ones in this group of 3, and you'll find the middle one. It also worked with other properties as well. Color, for example. If you had one of the 3 that was white and one of them that was black, the middle one ended up being grayish. Okay? And this wasn't uniform for all of them, but it did work for some of them as it's going through it. So mass appears to work out fairly well in terms of this. You can use the mass to make predictions about things. And the law of triads showed that you can take an average amount to get the middle one. So this was really the very first attempt to actually organize things, and it uses mass. The second one that we're going to mention also uses mass, and this is the law of octaves. So octaves, what number is associated with that? 8. 8. So the law of octaves says that if you order the elements, the 8th element in the sequence repeats the properties of the previous one. So if, for example, I take lithium and I count 8 elements based on the mass, 1, 2, 3, 4, 5, 6. Bless you. What's going on? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Lithium and sodium exhibit similar properties. If we count again, 1, 2, 3, 4, 5, 6, 7, 8, there's potassium. So if we have an order of these masses, the 8th ones end up repeating the properties of the previous one. Same type of thing. Now, in our modern day periodic table, this is seen by the rows. If you have this, then we count over 1, 2, 3, 4, 5, 6, 7, 8, replaces it there. So we see this repeating process. The main difference between what is up here on the board, on the overhead, and then the periodic table itself, is that the noble gases hadn't been discovered. So helium, neon, argon, they're not on this chart. And that's why you got to count just slightly different. This will throw me for a loop there for a second. Now, once you get to the heavier elements, it doesn't always work out correctly. But for the most part, this idea of 8 is a repeating process. This is actually where the name periodic comes from on the periodic table. This repeating of properties as you go through the periodic table is a periodic trend. Go through it. So that's the law of octaves. So the law of triads found groupings of 3 and then used 2 of them to predict the properties of the third. And then the law of octaves said that properties in general reactivity repeats as a function of 8 known elements. As you go through it. Do those make sense? Okay. So we're starting to see a bit of organization. Just like with our deck of cards, you can organize them based on suits. Okay. With elements, you can organize them based on their reactivity. With a deck of cards, you can do them numerically, 1 through 10, and then your Jack, Queen, King, and so forth. And in terms of elements, you can do it based on their masses. So these 2 approaches were actually very, very useful in Mendelev's creating of the periodic table. So we know that we can start grouping things based on properties, and we also know mass is an important thing. So these were the 2 basic ideas that Mendeleev used to build his periodic table. Now, he himself is a professor of chemistry, and he wrote chemistry textbooks in Russia. His story is pretty much the ultimate rags to riches story in the world. He was one of the later children, I think in a family of 8. They were incredibly poor because the father passed away, and then they lost their means of income. And this was in Siberia, Russia. So you can just imagine what it'd be like growing up there without money and so forth 150 years ago. And then eventually he went to school and showed promise. He became a professor. He came up with the periodic table of elements and became very, very famous because of it. Incredibly powerful in Russia in both academic and political circles because of it, and then well known throughout the world. Because this is one of the few times that scientific theory immediately became accepted. It wasn't like 2 decades of more science to prove a thought. This was an immediate thing. Once he released it, people immediately saw how useful it was.
Was there anybody else that was kind of on the cusp of putting it all together before
Absolutely.
he swooped in and took credit?
Okay. I'm going to preface this a little bit. Not swooped in. From all accounts, he did not know that the other scientist was working on it. The other scientist, though, you guys have never heard of. His name is Meyer. He's a German. And I've actually got a slide about it a little bit later on, so you don't have to worry about it now. But he actually came up with the same idea of ordering and making sense out of it, and the same overall periodic table. The difference is that Meyer published his like a month later. It was literally a month after Mendeleev did, and because of that, Mendeleev gets credit for it. In the scientific world, whoever publishes first ends up getting credit for it. It's kind of cutthroaty in terms of that. But that's why Mendeleev gets credit, and Meyer is a footnote. But I always make sure to mention him in lecture, because I kind of feel bad for him. He did all the work and then never gets the credit. So, how did he go about organizing these things? Well, he started with the basic idea of masses. Now, atomic number was not well understood at this point in history. So he's not using atomic number, he's actually using masses. And what he's going to do is he's going to organize mass going from left to right. So he's going to start out with a mass of 1. Okay. And then, secondly, if an element has the same properties as another element, he's going to put it underneath of it. So we get to element number 2, which at this time is lithium, because helium's not known. So the next mass we come up across is lithium. It has a mass of 7. But looking at the properties, it matches hydrogen. So instead of making another column going over, he's going to put lithium underneath of it. Okay? So I'm just going to change over and start writing out the symbols. Okay, so lithium was the next one that had a similar property, so he put it underneath. After lithium is beryllium. Beryllium does not show the same properties, so he makes another column, and he goes over one. After beryllium, it's going to be boron, different properties again, so we go over again. After boron is carbon, nitrogen, oxygen, fluorine. All of these exhibit different properties from one another, so he doesn't put any underneath the next one. So what he's doing is he's going left to right, organizing it based on mass, and then if a property repeats itself, he's going to put it in a column underneath. So after fluorine is sodium. Sodium does exhibit the same properties as lithium, so he puts that underneath. The next one that he has is magnesium. Well, lo and behold, magnesium exhibits the same properties as beryllium. So he puts that underneath as he goes through it. So what he's doing is mass across, properties going down. Now he continues on. Next one is aluminum, silicon, phosphorus, sulfur, chlorine, okay, as he's going through. Now if we look to the modern day periodic table, this is exactly what we've got through the first three rows. Hydrogen, and then lithium going across, and then sodium going across. This is without the 8th group because we hadn't discovered the noble gases yet. So we'll continue on. Okay, we've got potassium, calcium. And then the next one is number 44 here. Mass of 44. So if we look to the periodic table, that's actually scandium. I think it's scandium. But it hadn't been discovered yet. So we're just going to go ahead and put a dash there. This was really his genius when he did this. As he was organizing things, if for whatever reason, this is slightly off, he didn't have an element that fit, he just left this space. And he didn't fill it in. And he said, well, that element just hasn't been discovered yet. So go find it. And you'll find out it fits in there. So what he's doing is he's going through organizing things and then leaving these spaces. And this is really a huge, huge part of his theory. So for example, we have aluminum, and we have indium, but I believe gallium has not been discovered yet. So here's aluminum. See how it's offset? That's a whole nother set in there. So aluminum, and then underneath of that is this blank at 68. Hadn't been discovered yet. And then indium right here at 113. So whatever element this is, he said, okay, we just haven't found it yet. I'm going to call it, I think he called it ecasilicon. I think it's Sanskrit, actually, is where the name comes from, but not important. He left it blank there, and he said it just hasn't been discovered yet. And he went through, he organized them, and then if he didn't know something, he left it blank. And that's all well and good. But he went one step further. He said, okay, I know the law of triads and I know the law of octaves. If I have this element and this one's going to sit between them in a grouping of 3, I can predict the overall properties of it. So he took the mass of this, the mass of this, averaged them together, and he found out the mass should be 68. If you look to the periodic table for gallium, you find the mass is 69.7. Okay, well within the realm of being able to do that. What's going on here? Okay, a little out of order, but we'll come back in a second. So for example, acasilicon was the name of it, I'm sorry. He predicted these properties for it. So the atomic weight should be 72, sorry. The density is 5.5, specific heat, melting point, high. Very, very scientific. Color, this is my favorite. He predicted dark gray. The actual color is grayish white. I'm not sure what those are. They're not Crayola colors, but I assume they're the same. How they react with oxygens in a 1-to-2 ratio, the density of the oxide, how it reacts with chlorine, and so forth. So he made all these predictions. Then we look at the actual properties once it's discovered, and you see his predictions are right. We're going through it. So not only did he say, okay, we just haven't found this element yet. I know this element's going to exist, but you've got to go find it. Here's what you're looking for. You're looking for an element that's going to be dark gray. It's going to have an atomic mass of 72 and a density of 5.5. So then everyone went out looking for it, and when germanium was actually found, it matched up almost exactly. And he did this with several of the elements that were yet to be found. So imagine if we're in science now, and someone comes out with a theory. Okay, it doesn't really matter what the theory is, but a new theory. And then it says, okay, my theory predicts that this is going to happen. And then a week from now, this actually does happen. That adds a lot of support to your theory, doesn't it? And this is one of the reasons why he became so famous so fast, is because he was able to make these predictions, and then very quickly scientists found out his predictions were correct. Okay? So imagine, well, let's go to the extreme case. Imagine I had a theory that said that the stock market is going to go up 80% next week. Okay? And then it actually goes up 80% next week. You might think, well, that's cool. You know, that sounds like a good theory. And then the next week it says it's going to go down 20%. And the next week the stock market goes down 20%. Okay? What are you going to do the third week if it says the stock market's going to go up 80%? I'm going to put money into it, right? I'm going to believe the theory at that point. And this is exactly what happened. Each of these elements that he predicted, and then they became true, was another point in the right direction to understanding his overall thing. And this really goes back to the law of triads to explain how he did it. Does that make sense? The other thing that led a lot of credence to his theory was the thing we were talking about earlier. There was a scientist named Mayer, and he's a German scientist. And German scientists obviously worked with German. Russian scientists worked with Russia. There's a very large distance between them. You may not think of being a lot of distance between Russia and Germany, but that's a long ways, especially 150 years ago. And Mayer actually came up with a periodic table that was incredibly similar to Mendeleev's in terms of the basics and the general idea and so forth. But he published it, it was like a month or two, I think it was actually a month later, but it was over a calendar year. It was like December and January, something like that. So Mendeleev's theory actually gained more credit because the second scientist actually came up with the same theory at the same time, independently. And you can understand why that is. If people are working on the same solution and they find the same answer, then that's a good sign that you're on the right track as you're going through it. So Mayer, no one ever talks about him anymore. He's not really all that famous, but I want to give him a little bit of credit for his work. Because he did come up with the idea all on his own. Okay. So two things really added support to the periodic table of Mendeleev and propelled him to fame very quickly. It's these missing elements and his predictions of their overall properties, and then Mayer coming up with a similar periodic table at the same time independently. And after that, it was quickly adapted and used as we go through time. So this is actually a copy of a notebook page to where he originally came up with the idea. You can see the crossouts and so forth. But you'll notice lithium, sodium, potassium, this is going down, our modern day periodic table. Fluorine, chlorine, yeah, I don't know what those are. His handwriting's not so good. Okay, again, that is the halogens going across. Here are the oxygen family, oxygen, sulfur, selenium, tellurium, going down. So 16, 32, 16 is the mass of oxygen, 32 sulfur, selenium there, and so forth. So this is one of the original periodic tables as he wrote it out himself, working on the theory of it. Questions about that at all? So I don't think it came to him in a dream by any means. The theory of it is just too great, and then also the fact that it builds upon these previous theories. But that being said, it is pretty amazing that this idea came up like this, and then it was so quickly adapted and then used throughout time.
How long did it take from when you first started to publishing?
I don't know the answer to that.
I mean, was it like?
It's not very long. Not very long. Things fell in place very, very quickly. And I think that's part of the reason why some people still give credence to the fact it was a dream, because like, it all happened like all at once type thing. But yeah, I don't know the actual answer to that. So this slide we've already talked about. The law of triads, remember, is this grouping of threes. These are the vertical columns on the periodic table. So aluminum, gallium, indium is the most famous example of this, where he predicted the properties of germanium. Oh, wait. No, gallium. It must be gallium. I think he did germanium too. He did. So germanium is this one, gallium is this one. Where he predicted the properties of these missing elements and was able to predict them very, very well. And then second, the law of octaves is the 8 across, okay, where they're repeating on the 8th one. Now he didn't have a good 8th group to explain it, so what he actually did was he made this other 8th group of things that don't fit very well. But if we look now, we can kind of understand why. If you look, the 8th group here is iron, cobalt, nickel, and copper. So that's in the transition metal. That's the later part of the transition metal. And because of the way that the electrons are stacking, they do weird things that aren't expected there. And that's why you put them off to the end. So you can see both that law of triads and law of octaves present in the periodic table. Now, we have updated the periodic table since then. One of the biggest things is we don't actually use atomic mass anymore to organize the periodic table. We use atomic numbers. The reason for this is because of the presence of isotopes and the fact that a given element can have different masses. And as a matter of fact, two different elements can have the same mass. So that's one case. The other case that we don't often talk about is sometimes masses go out of order. So if you look here, iron is 55.8, cobalt is 58.9, nickel is 58.6. So nickel actually has a smaller mass than cobalt does, but that has to do with the isotopes associated with it. So it's just a better way for us to do it based on the atomic number. And since we're using atomic number to define identity of elements, you don't have any ambiguity there in terms of that. So atomic number is now how we base it, and that's why the atomic number always goes up by 1 as you go through the periodic table. We also set up the assignment of symbols. We've talked about this numerous times before, where not any symbol is just accepted. You have to have 1 or 2 letters for your symbol. The first one's a capital, and if there is a second one, then it's a lowercase letter as part of the symbol. Numbering of groups and periods. This actually has been done over the years. There's some argument about it, but I think we can all pretty much agree. So a group is the verticals. So group 1 is hydrogen and then everything going down. These groups are incredibly important because of the fact that they have the same number of valence electrons. Everything in group 1 has 1 valence electron. Everything in group 2 has 2 valence electrons. Now after 2 it gets a little more complicated, we'll talk about that later, but for now, just go with the fact that it gives you the idea everything in the same group has the same number of valence electrons. A period is the horizontal rows. I never liked the way they mark them on these periodic tables. But the period is the horizontal rows. This is the number of orbits it would take to draw your Bohr model. Chemists almost never deal with these. They're not interesting to us. The properties change greatly as you go across the period and so forth. We just don't care that much about them. But that's actually what they are. Maybe the only time in this class I talk about them, actually, because we don't ever do anything about them. Also, on the modern day periodic table, we have the atomic number and the atomic mass. The number is almost always above the symbol. The mass is below the symbol. You can always double check this because the atomic number is always the smaller of the two. The mass is always larger than the atomic number. Now there are other periodic tables that have all different types of things. If you go to the bookstore and you buy one of those laminated periodic tables, it's got like 100 different things on it. Everything else is useful to chemists for a variety of reasons, but we don't care about any of it in this class. All we really need is what's on the walls here. So I'll make sure you've got that as what we're working through things. Questions? Yeah.
You said everything in the same group has the same number of valence electrons?
Yes.
Is there any like correlation with everything in the same period?
No, there's not. I had to look. I forgot what a period was. See, we never use it. The horizontal rows, they have a name, but no, there's no correlation like that at all. There are some trends that have to do with it, but it's much easier to just remember as you move from left to right on the periodic table or something like that, not looking at like an actual period type thing. So later on in this chapter, we'll look at some trends. As you go across the periodic table, something happens, but that's not really having anything to do with the periods themselves. So now they're not all that useful. Yeah?
You said the periods were a horizontal line?
Yes.
Okay.
Yes. Now, the verticals are called groups or families. There's actually 2 names for them depending on how you're going to refer to them. The groups are numbered simply 1 through 18 going across the periodic table. There are some American periodic tables that have A's and B's, but we're just going to use 1 through 18. Okay, 1 through 18 for our groups. Now, families have names associated with them. So group 1 is the alkali metals. Group 2 is the alkali earth metals. Group 17 is the halogens. And group 18 is the noble gases. Those are the 4 that we're going to learn. And I'll give them to you again in the slide later on. But if you use group, you use a number with it. If you use family, then you use the name of the family. I'm not quite sure why we do that, but we do. I guess probably historical reasons. Okay. So, a few different ways to break up the periodic table as we're looking at things to understand properties and so forth. The first is this description of where the last valence electron goes. We have S, P, D, and F, different blocks associated with them, and here are the spaces for them. And I think we've talked about these before, so as you go through them, that's where they sit. So an example of this would be S elements tend to give up electrons. They don't want to hold electrons in, they give them up. P elements will generally take electrons and not give up electrons. So if you know if an element sitting in S versus P, you can kind of understand that. These down here, for example, tend to be magnetic. So if you have an F element, it tends to be magnetic. This is actually a huge deal in the world today because of what they call rare earth magnets. Rare earth magnets are actually really strong magnets. That doesn't really tell you much. They're the strongest magnets we have. And they're made up of rare earth elements. The issue is a lot of the rare earth elements, like 90% of them, are all in China. So the Chinese government has started locking down the sale of rare earth elements to other countries. And this causes problems in things that use magnets. One of the big ones being engines and power generation and so forth uses magnets. So if we can't get a hold of the rare earth elements, then we start to see problems in those types of industries going forward. A lot of my graduate work had to do with these rare earth elements. And we literally just called a guy in China, I don't know who he was just a guy, and say, mail us 6 pounds of this. Actually not 6 pounds, 6 kilograms of this. And he would wrap it in newspaper and mail it to us. I think it was all like under the table. But that 6 pounds of an element saved us money. So probably not 6 pounds. Let's say for every 100 pounds of elements we ordered that way, we saved enough money to buy a house. Hundreds of thousands of dollars were saved, not by going through the normal means, but by going to this guy. So my boss was really, really big in like ordering through, because we used a lot of this stuff. It is super, super expensive to buy it, especially through diplomatic means, and I'm sure it's only worse now. Now that China is clamping down on the sale of rare earths, I'm sure it limits it and it costs even more than it used to. Yeah, we literally would get a box, like a cardboard box, and there'd be like 6 chunks of rare earth metals wrapped in newspaper, in Chinese newspapers, and they were sent over. I don't know how my boss found out about the guy, but we did a calculation once, and I think over the period of 2 or 3 years, I think we saved almost $1 million by ordering through. That's how much rare earths we use. We used rare earths and everything, but just because we were doing that. So we never really asked too many questions. But those are controlled by China. They're used in a lot of advanced technologies, and that's going to be a problem going forward for the United States, I think. But we'll see. We'll see how it all turns out. You'll hear about it from time to time. And this is just because China controls so much of it. Okay, here's your official slide for the families of the periodic table. The columns are called families. And this is important because each family has the same number of valence electrons. And because it has the same number of valence electrons, we're going to learn it has similar properties to one another. So everything in the noble gas column, the noble gas family, doesn't react with stuff. That's a property of the noble gases. Halogens. Halogens are this family right here. They all react relatively violently with things because they have seven valence electrons. Alkaline metals are good for rechargeable batteries because they're in that family and so forth. And you just see recurring themes going throughout. All the groups do have names. The 4 that are up there are the 4 I want you to know. The other ones, some of them are used to some extent. Oxygen's family is called the chalcogens. Nitrogen's family is called the pnictogens. They're just weird names. The other 2, I would bet 99% of chemists don't know the names for them. I happen to because I did research with them. The boron family are called the trilides, and the carbon family are called the tetralides. So there is actually a name for every one of the non-transition metal groups going through the periodic table, yeah.
So when you see one that's in norm, like what exactly you want us to like study on it?
I want you to know that everything in that first column is an alkali metal. Everything in the second is an alkali earth. So if, for example, on the exam I said, what family does argon belong to? Okay, argon is right here. So what family would that be?
Noble gas.
Noble gases, something along those lines. Or which of these would be a halogen element? Something along those lines. And the reason why I want you to know them is because they are actually used in everyday life. Alkali batteries are the rechargeable lightweight batteries that are used almost everywhere. If you look at like AA batteries that are rechargeable, they're going to say alkali metals on them, or alkali batteries, because that's what they're made up of. Halogens, halogen lamps, halogen water treatment facilities, these types of things. Noble gases are gases that are used for a variety of things as well. So you'll hear them from time to time, and I think it's just good to know a few of them. But at the same time, there's no reason to know all of them. So the first two and the last two are the most common ones.
Is the number next to it the valence electrons?
For the first two it is, the last ones it's not. Let's do that once. Okay, so halogens. Let's figure out how many valence electrons the halogen family has. So to do that, what you're going to do is make a Bohr model for it. So let's pick the easiest one, fluorine. Okay, fluorine. Fluorine has 9 electrons. So you're going to start out here with 2 electrons in the first orbit. And then the second orbit, 1, 2, 3, 4, 5, 6, 7. Okay. So, this marker's horrible. Fluorine.
See it.
I want to redraw it. Back. I don't think this is helping. Okay. Fluorine has 7 valence electrons. If we go down the row to chlorine, chlorine is going to have 2, and then 8, and then 7 as it goes through it. So 2 plus 8 is 10, plus 7 is going to be 17. Chlorine is 17. So chlorine also has 7 valence electrons as you go through it. Halogens have 7 valence electrons. The noble gases have 8 as you go through it. It's just the way that it works out. I may as well show you the trick.
You said halogens had how many?
Okay, I'll come back. 17 and 18 is just counting over the columns. Is all that it is. Now that actually goes back to, I said very briefly that there's another way to label it that people argue about. What you're asking about actually goes into that. In the other system, the halogens are labeled as 7A and then 8A, and that tells you your valence electrons. But the official worldwide recognized system is the 18. Americans actually propose the AB, but I'm trying not to teach it because it's not everywhere. What was your question?
How many valence electrons did you say for a halogen?
Halogens have 7.
And nobles have 8?
Nobles have 8.
Okay.
Now here's the trick to it. You can draw out the Bohr model for these and you'll see that it works out. But everything in the first column has 1 valence electron. Everything in the second column has 2 valence electrons. Then we skip past the transition metals. This column has 3. This column has 4, 5, 6, 7, 8 as you go through it. So 1, 2, 3, 4, 5, 6, 7, 8 as you go across. And that's your valence electrons. We can do it with a quantum model as well. It's probably a good idea to just show it to you really quick. If I do chlorine, So chlorine with the quantum model, it's going to be 1s2, 2s2, 2p6, 3s2, 3p5. So looking at the highest number here is 3. So 2 and 5 gives you 7 valence electrons.
So when you, one of the questions on the assignment was how many valence electrons was in the equation. You count the last two?
No, you count any of them that have the highest number here.
Okay.
Okay. Yeah, that'll work. That'll work. Let me double check that real quick. Bromine. So bromine is 1s2, 2s2, 2p6, 3s2, 3p6. What's after 3p6? 4s2, 3d10, 4p5. So 2, 10, 10, 20, 35. Yeah, 35 is bromine. Okay, so here, for example, for bromine, the largest principal quantum number is 4.
Mm-hmm.
So it's this and this.
Okay.
Of course, the monitor is in the way. So if you add those two together, you get 7 as well.
Okay.
Does that make sense for everyone? Yeah, okay. The reason why I'm spending time on valence electrons is in the next chapter, when we get to chapter 4, when we start talking about why elements do what they do, 99% of that is valence electrons. So understanding how many valence electrons something has really is the very beginning of understanding why things do what they do. And you can't really oversell the importance of valence electrons. Okay, oh here, this will be perfect. So, as I said, elements in the same family exhibit the same property. So you can go online and find all different types of things. I just found a YouTube clip here. See if it will get past our Ziploc commercial. Come on. And what they're going to do is they're going to show the reaction of alkali metals with water. So here are the different alkali metals with water shown for different scale. The last one, francium, is faked, by the way. I don't think it's even legal to do francium in water in most places. So we start with lithium, put it in water, and it sets itself on fire. As you move down the periodic table, this reaction becomes more and more violent. So the next one up is sodium. Sodium reaction.
Does it eventually burn itself out?
Yes, eventually it all gets consumed. Actually, that one's not very good. This one's kind of neat, this next little picture here.
One drop of water.
1 drop of water on sodium, yep. Okay, a huge chunk in water. Please do not ever do this. I have done this, but obviously if you scale up, whoa, so does the explosion.
They probably killed the fish.
Would that be the kind of chunk you get from China?
Well, yeah, that would be the kind of chunk we get from China. Okay, potassium. Okay, I won't do that. Rubidium. That takes some nerves to stand there and talk about that, by the way. This last one's francium. It's obviously faked and everything because you can imagine as you go up, you get an order of magnitude more reactive. I don't know if this is even to scale or anything. The video you saw with the bathtubs, they did a francium one, but they faked it. And they didn't tell people they faked it, so we don't like to show it anymore. Francium's radioactive. I don't know how much it would take to do that. But if you can imagine, you could do that with francium, actually, as you go through it. So, family properties are the same going down the periodic table. Reactivity of water increases as you go down the periodic table. There's examples of it except for the francium, which I find kind of fun. And we'll see everyone next time.